All right. So, so as I'm making sure that YouTube is going, I'm just going to say to remind everyone that there's a quiz that is happening today. So it's going to happen. Okay, good. So it's streaming on YouTube, which is great. So there's a quiz that's happening today that is let's see, so get that volume bar away. Okay, so that's happening after class. It starts. I've opened it on Canvas. It's going to be on Canvas. Hopefully, you've all have taken a quiz before on Canvas in a previous course. I'm opening it at 2:30, which is 15 minutes left in class, and it closes at 4. You'll have half an hour to take it as soon as it opens. This first one we call it quiz 0. It's worth a quarter of any of the other quizzes, and we pretty much expect everyone to get full points and everything. It's going to be about what's on the syllabus, and you can use the syllabus to answer it. This is kind of just a warm up to make sure everyone's used to it, especially me and the TAs. And I think we asked you a question to try and write something in math just to see what, how comfortable you guys are with that, to let us know what sort of questions we think is fair to ask on future of the quizzes. It'll be important to be able to write stuff in the language of the mathematics for this course. So we'd like to be able to do that on the quiz. So it'll take a bit of time to try and do that and get familiar with it. So when you have to do it next time, there's not a pressure to kind of figure out how to do that. What if you have to work immediately after this class? So it's open at so it's okay. So it's an interesting question. It's open until 4. It opens at 2:30. I don't think it should take you longer than 10 minutes. I'll consider opening it at 2:15 in the future, so you'll have the 30 minutes inside class, although I won't stop the lecture until about 2:30 on those days. But that's a good thing to figure out in this case. I don't think it'll take you longer than 10 minutes, so you should be done by 2:45. But in the future, I don't want people to feel rushed and have a smaller thing. So that's a good question. That's why we're having a quiz 0. Great. So I don't want to have it open for too long, because then because then people start talking and all of that stuff. All the quiz be open booked notes or just this one? My rough plan is to have them to be open book. Though I haven't totally decided. So I'll probably have them be open books, so that you shouldn't need the books. In the past, I let people bring in maybe a 1 page of notes or something like that. I think that's still a good strategy. So maybe I'll say you can bring in one, because it helps you learn to actually create this 1 page of notes. So maybe I'll say you can do that, and then you have to turn that in. I'll think about that. If you've got a big preference for that, so let me know. I might lean towards allowing 1 page of PDF of 1 page of notes that you can turn in with the quiz. But I don't have a way of enforcing this stuff, and I'd like you to learn it. And I'd like this be a way to check if you've learned it. So let me think a little bit about the most effective way to do that. I don't suspect that they're going to be hard, but I don't want you not to open the book until the quiz starts either, because that's not a good strategy for pretty much anyone. So that's a great question. Let's see how this first quiz goes, and then we'll make adjustments that we'll try and set for the quizzes that you'll actually be tested on knowledge from the class. So great. So we're going to continue our probability review, and this is kind of will be the last reviews of the basic probabilities, and again go a little bit faster than some other lectures. Then we'll talk about Bayes' rule, which you've probably seen before, but we'll go into in maybe a bit more depth than maybe how it was taught in the undergrad probability course, or maybe about the same depth. But it turns out it's pretty important, and we'll spend a couple lectures on that and its implications and into data analysis. So great. So what we are talking about today we're starting again with probability, so density, so functions, and this has to do with when you have continuous, so random variables, right? So we have a continuous random variable, and we're going to say it goes from some sort of domain into into another domain, and we're going to in general say this is this set of real numbers. Okay, and so this and probability density functions is what basically allows us to define probability properly when you have continuous random variables measuring things like time or amount of rainfall or so something like that. So these are defined then. I'll write lowercase f sub x. X is the random variable, is then going to be a function from R in this case, where it's the space of the output values of the random variable function. So again, into R, which is going to be the positive, and these values have to be greater or equal than 0. Right, so like it has to satisfy things like a probability, except I can't define it. It's not really well defined, or it's a 0 for any particular single value. Right, this was the challenge. So we instead would like to define that the probability that we have that our random variable is inside some sort of event. Right, now A is an event, which is going to be A is a subset of the domain of the range of the random variable, the domain of this probability density function. Then I can define this by integrating over this, right? So I can say for all the values in A, then I can write f of x of these outcomes. I can look at the value and I can do an integral over all the continuous things in this event. Okay, so remember we had this train leaving example between this time. I would integrate over that time, say the first 40 seconds, and this would tell me the probability in the zone. I can't define this for any single value. This would be 0, but over some range of values, I can now define this probability. So this is a little bit, okay, so you have to use this. We have this because we have to effectively define this with calculus instead. What I think which is a little bit more natural, and I think works with kind of seamlessly with both the continuous and the discrete random variables, is instead the cumulative density function. Okay, and so this is often called the CDF. Okay, where this one was the PDF. Okay, so the cumulative density function is then a capital F of x. And so I can define it for some value t. And this is now equal to the integral from negative infinity up to t, right, of this value F of x. dw. So now I can again define this for a single value, right? Where before the probability density function, I could evaluate a value, but it doesn't define the probability. Now this is defining is equivalent to the probability of some sort of event x is in this event a of t, where a of t equals to this range up to the value t. Okay, so I can define an event up to the value t, but it allows me to kind of have this be a well-defined probability associated with each of the values. So that means that this value is always in 0 to 1, okay, and it's always monotonically increasing. Okay, so as I get a larger value of t, this value has to increase because this range a of t here, as t increases, this range has to also get larger, right? So okay, so and then I can get back f of x at a value w. If the CDF is differentiable, then I can write d of f of x at w dw. So I can take the derivative of this cumulative density function at this point, and I can get back the value of the PDF. So this means even though the PDF is not telling me exactly some probability at a single point, I can still evaluate it and it still has a value. And these values, I can still compare these values to each other. So I can say this is more likely than that, but I can't say it represents an actual probability. So yeah, so I next want to kind of talk about a really important example, which is a normal, so random variable. Okay, this describes a probability distribution. So this associated with the random variable x, right, which is going to be, it's going from, so I will say, and the way you'd write this is that x is drawn from a distribution associated with a normal random variable. It has some parameters mu and sigma, which I'll explain. Okay, and so this tells me the probability distribution of this random variable x. Okay, and so then this is defined as this is defined as f of x at some value of 1 over square root 2 pi sigma x, and I'll explain what this notation means. The values, well, let's write this more generally. This w minus mu squared divided by 2 sigma squared. Okay, so this, if you haven't seen this form, it's going to look kind of strange. So first, x of some value x is equal to the e to x. So when you're writing something e to some power, and there's a lot up in that power, the exponent, it's kind of hard to see what's in the exponent and what's kind of multiplied by or something like that. So if you write x, then you can write the kind of the parentheses around it, so it's clear what's in the exponent. So that's what that notation is meaning here. Okay, and so what is going on here? First, let me draw a picture here, and then I'll show you the actual plot in Python. What's going on here is that there's some mu, which is like a mean value, and so the distribution is going to be centered around this point mu, right? So this is a value in the values in the real numbers. And then there's going to be some sigma value, which basically tells me how spread away this is from this mean, roughly. And then the distribution itself is going to look something like this. Let's see, and I'm not, it's not a perfect drawing, but it's going to be centered around this mean value, and it's going to be spread out basically roughly by this sigma value. Tells me how spread out it is. Okay, and so that's roughly what the picture looks like. And if I and it integrates to 1. It's a probability distribution. So this term here, I put this in front. I'm basically dividing by a value to make sure the integral is 1. That's why I have that term there. The important part is the exponential part, and it's saying as what's going on is as I get further away from the mean, then I'm exponent to a value which is negative, right? So I'm negative. So as I get further away, I'm taking exponent to a value which is negative, and it's decreasing as I get further away. Okay, so that's how to think about what's going on here. And this is a standard way to model noise in data. I think the value is at the mu value, the mean, but I'm not really sure. And so it kind of, this is the distribution of where it might be. This turns out this will show up over and over again in the course. Okay, I'm going to switch my screen share a second to go to view how to plot this. And screen share, Chrome. Okay, so now you should be seeing an IPython notebook. So if you go to this URL, collab.research.google.com, you can set this stuff up. You can type Python into the notebook here, and then you basically press like shift return, and it compiles, and it runs it. It doesn't compile it. It's just the time compiling, runs it in the browser on Google servers. So you don't have to install anything. It's pretty straightforward. And if you haven't done Python before, the reason Python is so popular with data analysis is that it's got a huge number of really useful libraries. We'll go through some of these more in detail later in the semester. But this is matplotlib is the most common plotting library, although there are some fancier things afterwards. That's what I'll use to make this plot down here. SciPy has a lot of great, fairly standard functionality, including like the normal distribution. This is kind of the stats part, and this is the normal distribution. NumPy can handle vectors. In this case, we're just using it for plotting, but it'll be very useful for linear algebra. And this is a built-in kind of math thing because we need this for the square root. So I can set, in this case, set the mean equals 0, the variance equal to 1. Then sigma is a standard deviation of the variance. We'll mention this, and I plot it from -3 to 3 with 201 kind of values I'm plotting at. It doesn't do a continuous thing. It does a discrete thing. And then I plot the PDF and the CDF of the normal distribution. These are a built-in function that I'm calling right here. And I plot the legend and PLT show, and it generates this plot. Okay, so the blue one down here is the normal distribution centered at 0, and the orange one is the CDF. So the CDF goes from 0 up to 1, and it's always increasing, and its slope is steepest where the value of the PDF is the highest, right? Because if I took the derivative of the CDF, I'd get back the PDF, right? So as it goes out further, the slope is basically 0 of the CDF because the value of the PDF is basically 0. Okay, and I can change the mean, right, to 2, and I can rerun it. Oh, it shifted everything over by 2, right? -1, okay, and I can change the variance to 2, and this should make it flatter, right? Let's recenter it, right? See, it's now flatter than it was before, but it should still integrate should still integrate to 1 if I did. Oh no, I didn't normalize inside of here, so that's what's, Yeah, so I'm not normalizing inside here, so it's getting flatter, but I didn't plot the normalization here, so it's not actually shrinking. So it's not integrating to 1 anymore. How I plotted this. Sure. So okay. So this is pretty simple how to do. You know, we'll probably do something in a couple more lectures when we do linear algebra, where I'll ask you all to kind of look at collab ahead of time, and maybe we'll just go through all examples jointly. But this one, I just want to show you how to do it. Your first homework assignment, you're going to actually plot something very similar, just to force you to do it. But again, should be pretty easy and straightforward. So great. Okay, so let's get back to the lecture. And screen share. Okay, great. Okay, so this is the normal distribution, and you know, you can draw the CDF. One thing about the PDF in this case, I can compute this function to actually give me the value. The cumulative density function has no closed form, which means I can't actually write down an expression with standard operations that I can evaluate what the CDF is. Now that's built into a lot of these libraries, so you can pretend like you can do it, but it's just stored as a table effectively. So that's a strange thing about this. But in other distributions, the CDF has a closed form, but the PDF does not, right? So you have to sometimes go back and forth with these through calculus. Okay, but for the most part, we're only going to need the normal distribution in this course. This really is the central thing. I'll mention a couple of other distributions at times, but the normal distribution is really the workhorse, and we'll explain why over the next couple of weeks, why it's like so, you know, why it shows up all the time. So okay, great. Let me make sure the chat's open. Okay. Oh, great. I couldn't see the chat when I switched screen share. It closes it. Okay, so it's sigma where the line goes to 0. No, sigma, yeah, so sigma is about halfway down, about how far out it goes. We'll explain exactly what sigma means. And right now it's a parameter of the distribution. Yeah, great. Yeah, okay, good. Looks like everything's answered up there. Okay.
Sorry, volume bar is shown.
Okay. Okay, great. So, okay, so the next, so we'll basically explain what the mu and the sigma stand for next. So the expected value basically is what mu was in the normal distribution. And the expected value is a kind of a function that's you apply on top of a random variable, right? So again, we have a random variable that goes from some domain lambda to omega, and will basically be considered when omega is kind of equal to the real values. Although this actually works when it's kind of more generally, for instance, multidimensional real values, you can think of it the same way. Okay, so, and then the expected value of x, we'll write this as e, and it's a special function, so we'll use the square brackets, although notation kind of varies for how to express this. And for a discrete random variable, it's just going to be all of the possible values that this x can take, or inside this this sample space. Okay, it's the value it takes times the probability that x is equal to this value. Okay. So I'm just basically, what this is it's a weighted average. Okay, I know that these terms, the sum of these terms kind of is equal to 1, right? So I'm multiplying each value by something less than 1, and then I'm adding adding all of these things up. So it's kind of a weighted average based on the probability. Okay, so I can think of having some, kind of probability distribution that sits on top, here. Maybe it's the normal distribution, maybe it's bimodal like I've tried to draw here, right? So this is the probability distribution. And what this does, it's an average. So I'm trying to pick a point so that it balances under this point. So if I put my finger under here, then it'll have equal weight on either side, not the total amount of weight, but the further out it goes, it counts more. So if you're like a waiter or waitress in a restaurant and you're balancing a tray, there's a bunch of stuff on it, you want your hand to include the mean, the expected value in it, because that's the center of mass, so that it balances on there. If the mean was off your hand, the tray would tip over. Okay, but if the mean is inside where your hand is, then you've captured everything. This is a continuous picture, but you can, same thing with discrete. And so with a discrete random, or with a continuous, so this is discrete, this is continuous, then I basically have to replace the sum with an integral. Okay, so I put an integral over the entire domain, and what I evaluate is then the value again. Now I replace the probability with this PDF. Okay, so now I just integrate. Now it's a weighted average, but it's an integrated weighted average. Again, the same thing as before. Now I basically have the integral, the integral of this term. This is equal to 1, right? So remember, the integral of the PDF has to be equal to 1, so it's again a weighted average of the value that it takes. Okay. Yeah, so this picture, this is E of x, and this would be, that's the picture of the probability distribution f of x right there. Great, so this is the kind of the expected value. Let's go through a simple example. So let's say I have a 6-sided die, and it's a fair 6-sided die, right? So that means the domain can take on values 1 to up to 6, right? Can take on the 6 different values, each of them, right? So the probability that, and so there's some, this corresponds with the random variable x, and the probability x equals to I for I equals 1 up to 6 is going to be equal to 1/6. It's a uniform probability. Each of the 6 sides is equally likely. Okay, so this is kind of a fairly kind of standard setup of random die. What is the expected value that is rolled? Okay, so now the expected value of x is going to be the sum. Let's label these guys as W1, W2, up to W6. Okay, so the sum of Wi, or Wi in this, make sure this is clear, Wi in this domain, so it goes from 1 to 6, and times the probability that x is equal to Wi. All right, and this is the value 1 times 1/6 plus 2 times 1/6 up to 6 times 1/6. All right, if I add these all up, turns out this is equal to 21 divided by 6, which is equal to 3.5. Okay, so if you roll a die, the expected value is 3.5. All right. Okay. So hopefully if you've taken probability, you've seen this before. This is clear, but this is kind of a very important concept. Okay. The next kind of one of the most important properties of expectation is that it's a linear operator. So there's a property called the linearity of expectation. Okay, and so this says that these linear functions are things that you can kind of take the multiplication and addition and factor them out of the function. Okay, so if I have random variables x and y, and I've got a scalar value alpha, then I can do something like so if I have an expression where I've created this other random variable, let's say this term in here is z, right? Z is another random variable I'm taking the expected value of, but I know I can write it as alpha times x plus y. Then I can factor this out times alpha expected value of x plus the expected value of y. Right? So okay, so I can so there are two things that have happened here. I've done them at the same time, but I've factored out the scalar term. Like there's a factor 2 in front. I can factor this out, and I can pull that out of the expected value. And if there are sum of two expected values, I can pull that out as well, right? So if I have this sum, I can take that outside the expected values. So this is now useful if I know for the random variables x and y, I can individually compute their expected values. Then I can plug that in and solve it for this complex composition expression, as long as it's addition and multiplying by scalars. Multiplying by x times y, I can't factor out. I couldn't factor that as expectation of x times expectation of y, unless these are independent, right? If they're independent, then you can do this, but only if they're, so only if they're independent. So okay. So this is kind of we will see this property linearity of expectation manifest within a bunch of the analysis we'll do later. It's kind of the basis for most of data analysis, in fact, because really what you're doing is you're going to make a whole bunch of these observations of data, and you're going to kind of average them. And an average is really just the sum and multiplying by 1 over n or something like that. And so that it all comes, you can look at just the expectation of the individual observations and kind of do the calculations. And this will come up throughout the semester. This is kind of the base of what's going on. And the expectation is like, what is the central value? What is a single value estimate of what's going on, right? So this will represent the modeling that we do. This will be the best model in some sense. And we'll discuss variance on this, but that's a high-level picture. Okay, so let's go through a simple example. So, so let's say I want to measure the average height. Okay, and so let's say height of someone, of say some basketball player, to measure their height, you need to know their true height if they're in their bare feet, and then the height of the shoes that they're wearing. And different basketball players, some like to wear shoes that are like 3 or 4 inches, that have 3 or 4 inches of lift, because then they're taller to get the rebound. Others want to be lower to the ground to be faster, something like that. So there's some variation in how you measure the height. You need their true height and then their height with shoes. Okay, so let's say the barefoot height of a of just a normal person. I think I've got the height of like an average man. If men and women have different average heights, and it'd be multimodal otherwise. So let's stick with the simple example of men. And the PDF, let's say for the average height of a man, has a normal random variable, normal with a mean of 1.755 meters, and the standard deviation, the sigma value, which we won't need, but I'll write it here anyways, is 0.1 meters. Okay, and the normal random variable, I know that the expectation of this is exactly its mean, is the mu parameter. So I know that this is 1.755 in meters. Okay, but I also want to model the height of the shoes. And let's say the shoes, there are 4 types of shoes kind of people wear, just to kind of show you can mix continuous and discrete things here. And so a shoe, height, let's say this is a discrete random variable. So it can have 1 centimeter, 2 centimeters, 3 centimeters, or 4 centimeters of height added. Okay, so let's say this. And so this happens 1/10 of the time for 1 centimeter, 1/10 of the time for 2 centimeters, half the time for 3 centimeters, and 3/10 of the time for 4 centimeters. Okay, so people like to have lifts in their shoes, according to this example. Okay, so now what's happened is we want to find out the average height of someone, let's say in meters, but we need to combine the effect of the shoes and also let's say we want to do this in centimeters, right? So we need to combine the effect of the shoes and the height of the person, but we need to change the units, because if you notice what's going on here, this is in centimeters and this one's in meters. So to change the units is going to be a scalar, right? So now I can say the expected, let's say value of x is expected, and this should be in centimeters, should be the expected value of the person times times 100, because there's 100 centimeters in 1 meter, plus the height of the shoes. Okay, to calculate this, I can decompose this into 100 times the expected value of the height plus the expected value of the shoes, which is already in centimeters, right? So this ends up being 175.5 centimeters plus the expected value of the table turns out to be 3 centimeters, and I get 178.5 centimeters. Okay, so I can compute the expected value of the table by averaging up this weighted average. This was 0.1 times 1, 0.1 times 2, plus 0.5 times 3, plus 0.3 times 4. If I add those all up, and then it turns out the answer is going to be 3. Right, and then that allows me to solve for the expected value using the table. And so I can decompose these and calculate them separately and add them back together again. So this turns out to be very useful, very, very powerful trick. And this is because of the linearity of the expectation operator. Great. So okay. So that kind of explains what the normal distribution, what this mu value was. That was the expectation. The expectation of the normal distribution is one of the parameters. There's the mu parameter, that's the middle. That's where it balances on either side. It happens to be symmetric, and so that should make sense. Okay, so what is the other parameter? It turns out to be standard deviation. And to explain that, we'll actually explain what is easier to work with most of the time, which is the variance. Okay, so the variance of again, I'm going to have a random variable x. Okay, and a variance is another operator like the expected value. I'm going to write it like this throughout the class, variance with square brackets of x. Okay, and so I can define this in basically there are two common forms that are both sometimes useful, and it's defined through the expectation. So it's again a certain type of weighted average here. It's of this random variable minus the expectation of that random variable again squared. Okay, so this looks weird. I've got this operation, the expected value, in here twice, but it's important to note that this term is actually a scalar. This is a fixed quantity. So this is a fixed quantity. So when I'm doing my integration, right, the expectation operator has an integration. I'm the one on the outside. When I'm doing that integration for this expected value here, then I should that quantity is fixed, so it can kind of be factored out as a constant. I'd have to pre-compute it doing the expected value, but then I use it in the variance. Okay, and so there's another common way to write this, and this is equivalent. You can write it as the expected value of x squared minus the expected value of x, this quantity squared. Okay, so now, at this point, you need to realize the linearity of expectation means you can factor stuff out of the expectation, right? But I can't factor out kind of this squared term here. If I did, the variance would always be 0, right? I can't factor that out. I can factor multiplying by a scalar or adding another random variable, but not multiplying by a random variable here. Okay. So these terms are different from each other, and it's one reason you write this way is so you are forced to realize that. But okay, so the two terms you're subtracting here, and so let me just quickly derive why these are equivalent to each other. I think this is kind of informative. So let's expand the x minus expected value of x, this quantity squared, just to kind of see what's going on here, what you can factor out of expectation, what you can't. Okay, so this is a polynomial inside here, so I'm going to kind of open up this quadratic thing here. And so I'm going to do x squared minus 2x times the expected value of x plus the expected value of x squared, right? This is, right? So I've just taken the kind of parentheses, the expression that's squared, and I've expanded that out here, okay? And now I can do some factoring of things out. I'm remembering now that that this term and also this term are constant scalars, which means I can factor them out. Also, this 2 here is constant scalar. Okay, so that means I can use the linearity of expectation to say x squared minus 2 to the expected value of x, which I factored out, but then I have to write the expected value of x here. So this guy is the part that's not factored out, other than by the sum, times the expected value of x. Well, this whole term is a constant, so I just factor out that constant value. Okay. Okay, so I've reduced the expression. Now I realize that the middle term has the expected value of x times the expected value of x, which is exactly the term on the right. And I'm subtracting 2 in the middle and adding 1 on the right. So this just simplifies to kind of keep the left term here the same. And now I cancel out the right term with one of the two terms in the middle, and I get just expected value of x squared left. Okay, and I've derived the equivalence between these two. Okay, so that's why these are the two kind of common forms of the variance here. Kind of gives you a sense of what you can and can't factor out of linearity of expectation. So is there a similar linearity sort of expression with variance? Can I factor out something with variance? Turns out it's not quite the same here. If I have a random variable x and a scalar alpha, then variance of alpha x equals alpha squared variance of x. Okay, so I can still factor out the scalar, but it gets squared when I factored it out. If you notice, all the terms in the expected value have the squared component to them. So I've changed the units from the original units to the squared units. And so when I factor out the alpha, it becomes squared. Okay, okay, so this leads us to say, well, if it's the wrong units, right, the variance is not in the same units. It's not in centimeters, right? If I had a random variable in the centimeters of height, then the variance is not in centimeters. It's in centimeters squared. So then there's this deviation, which is another expression. And usually you write this as sigma sub x. It's the standard notation for this. And it's just the variance of x, the square root of it. Okay, so now the units are the same. Okay, and if I go back to where I drew this picture, right, the sigma is saying how far it goes left and right, and the mu is kind of the mean value. These are the same units, so it makes sense to draw a sigma on here as basically how far I've stretched this thing from the mean. Whereas if I drew the variance on here, which is the more common notion you work with kind of mathematically, but not actually draw, it would make sense. It's a squared quantity. So if I change the units, then the variance changes in a strange way. I can't draw it in the same picture here. It would be like an area term even, which I don't have a good way of expressing that. Okay, so that's why we have this standard deviation instead. Okay, great. So let's go through a simple example. Let's go back to this table with the shoes. Okay, we had s equals 1, s equals 2, s equals 3, s equals 4. Okay, and this happened 10% of the time, 10%, 50% of the time, and 30% of the time for 4 centimeters. Okay, and so we had calculated before that the expected value of s was 3, and this is a fixed scalar, right? So if I want to write now the variance of s, I can write this as the expected value of s minus the expected value of s, quantity, this whole quantity squared. Okay, so what I want to do is now I want to expand this out in the expected value. So this is going to be a sum from s equals 1 up to 4. Okay, and I want to plug that in times the probability. So of the probability that s equals kind of basically I times this value of I minus the expected value, which was 3, I can plug in the expected value squared. Okay, so let's actually write out the sum. There are only 4 terms here. This is 0.1 times, okay, this is 1 minus 3 squared plus 0.1 times 2. This is now going to be 2 minus 3 squared plus 0.5 times 3 minus 3 squared plus 0.3 4 minus 3 squared. Okay? So I've just expanded this out. Now the value, remember, was this complicated expected random variable, which was s minus expected value squared, but that's the whole random variable. So that's what's get plugged in. You know, this is the whole random variable. When I write that out, its value, it takes on that whole form. And so I get, and this then takes on these values. In this case, it's 2 squared, which is 4. Which is 4. This is 2 minus 3 is -1 squared is 1. 3 minus 3 is 0 squared. 4 minus 3 is 1 squared. Okay. So now I add all these up at 0.1 times 4 plus 0.1 times 1 plus 0 plus 0.3 times 1. Like this. Okay, so and I add those up, and I'm eventually going to get, let's see, it turns out to be 0.8. Yeah, 0.4 plus 0.1 plus 0.3, 0.8. Okay, so the standard deviation, or the variance is 0.8. Okay, that's a value I get, which is in centimeters squared. And then that means that the standard deviation is square root of 8, which in this case is larger than 0.8. It's about 0.894. When you're something less than 1 and you take the square root, it moves closer to 1, which is larger. Okay, so I've made this standard deviation is about 0.9 centimeters. Okay, with the mean of 3 centimeters. So this. Sure. So okay, great. So this is all kind of standard definitions, but it's kind of useful to see how these things are put together. Okay, a couple more things I want to cover before we'll break for the quiz. I'm a little behind time. Okay, let's get through this. So the covariance of two. Now I have 2 random variables. So x, y are both random variables. Then the covariance is another operation which takes in 2 random variables and say how they vary with each other. And I'll just write down the definition here. X minus y, sorry, let's see, the expected value of x, y minus the expected value of y. Okay, so this is an expression, but now the outside, so these guys again are scalars, and I need to do the work by taking an expected value over both x and y at the same time. So they can take different values, they may depend on each other in some way, and I can, if I have this information, say a joint table between both of them, then I can again work this out this same way I did in the previous example. Okay, and this says if it's high, then they both get large at the same time, or they both get small at the same time. Then this would be a large value. It can be a negative value if when one gets large, the other one gets small, right? Then the deviation from the mean is positive for one, negative from the other. Positive times the negative value is negative. Okay, and so if it's negative, they're one gets large, the other gets small. If it's positive, they both get large or both small at the same time. Okay. Okay, so the right way, just add it in. Hopefully you've kind of seen that before, or you'll see it as you're taking this, but it's not difficult hopefully not too difficult of a concept. What's important is to think of joint random variables. And that's really what we need to define the covariance. I have two random variables that it's kind of like a multi-dimensional table. They're both affecting each other in some way. Okay, and so so if I have joint random variables x and y, and I don't assume that they vary independently of each other, then I'm going to have a joint PDF, which is going to be some f of x, y, two random variables. And so this will go from domains domain of x, domain of y, to again a value between 0 and infinity. But this should be, again, if I integrate over these, it's going to be so in the discrete case, then I'm going to have f of xy. Some for lower, these are lowercase. The subscripts are uppercase x and y's. Then this is going to be equal to the probability that x equals x and y equals y. In discrete case, I can define it that way. In continuous case, I have to define it through calculus again, through the conditional probability and so forth. But I can define a probability density function in this way. It tells me a compare, some value which I can compare against each other. Oh, let's see. Oh yeah, so there was a question before about the variance. In case that's unclear, what does it tell us? It tells us how spread the data is from the mean. In fact, it's going to, we'll see examples of this over the next couple of weeks before we get into kind of the classic modeling like regression and clustering and stuff. But we'll see that it's effectively our sum of squared errors measurement of, if we model the data just by the mean, what is the sum of the squared errors that we have? That's going to be a measurement of how much error we have with the single value measurement. That's another way of thinking about it. So we can again define the probability mass function. So we know this integrates the one and all the, if I decompose into pieces, those, you can add those up, just like it works like probability. There's kind of some important other definitions to go through for the marginal PDF. Even if I have a joint random variables x and y, I want to find the marginal PDF of just x if I ignore the contribution of y. I want to marginalize that. Like if you have some marginal, you can marginalize a group of people by ignoring them from the census or something like that. Not that you should do that, but think of that's what you're doing with this variable y. You're marginalizing, you're factoring it out. And so how you define this is for all values y in this domain, you look at the joint PDF xy, and you're basically summing over those contributions. So in the discrete case, again, this is the probability of x equals x, and y equals y. Okay, but I'm summing over all the possible values of y, and because they're distinct values, I can add them up, and that gives me the value for x. So it's just like if we have this table, we're adding up all the contributions along the column for that value of x, factoring out the different choices of y. Okay. So and then in the continuous case, then you would define this with probability instead, or with calculus instead. You need to take the integral of f of xy dy. Okay, so you just define this with probability instead, with the integral instead for the continuous case. What's common between both of them is the marginal CDF. Okay, I'll write this as uppercase F, uppercase X and Y. And this is defined, well defined for distinct values, lowercase x and y. And this is equal to the probability that x is less than or equal to the value x and y less than or equal to the value lowercase y. Okay, so both of those conditions are true. That's what this is saying. And so I can define that through a sum over a probability table, or over, or I can use kind of calculus. I can integrate over both x is less than lowercase x and y is less than lowercase y. Okay, so a concrete example: if you had two movies with an average review score of 5/10, high variance would mean a lot of people loved it and lots hated it. With low variance would mean everyone agreed the movie was, yeah, great. So low variance would mean there's a lot of agreement on the score of a movie, and a high variance would mean there's a lot of variation on the score of a movie. Yes, that's a single value way of describing it. There are other ways. It could be multimodal, and there's other ways to describe this as well. Yeah. Good. Okay. So let me maybe go. Yeah, so let me just say the conditional. So we can say now a couple of things. So random variables x, y, they're going to be independent if and only if f of x, y, xy is equal to f of x multiplied by f of y, y. So if I can factor out this joint PDF into the product of these kind of marginal PDFs, then that's what it means to be independent. That's another way to see this. Okay, and then there's one more definition I need to give you guys, which is the conditional distribution. Okay, and so that's going to be kind of effectively in the discrete sense. We're gonna write this as f of x given y. Okay, of x given y, and this is kind of effectively the probability of x given that y equals to some value. In the discrete sense, we can write it this way, or in the continuous, more generally, we can write it as f of x, xy, right? This joint distribution over the marginal distribution. Okay, so we did an example of this with the table before when we were verifying the definition of, I'm going through an example of conditional distributions with the table. So last week. Okay, so there's another example or a couple examples I want to go through on this, but I'm going to stop now because we have a quiz today. So with the quiz, it should be open on Canvas. It's from now until 3:30 are going to be my office hours. And so if you have any questions that come up on the quiz, you can ask me about it. We'll go through the other examples at the beginning of the next lecture. So I'll be open on Zoom if you have any questions, or if you just want to ask me some questions during the office hour until 3:30. Hassan will make sure he's on here at least until 4 if there are any questions about the quiz. And I'll kind of be on here. I kind of have another meetings. I'll be kind of monitoring things at the same time.
Sure.
So, but if you want to ask any questions about this, Also, there was a really cool conditional probability puzzle that was posted. I just saw on the internet yesterday. If you ever heard of the Monty Hall problem, there was a new version of that came out that's a bit more complicated, but maybe even more interesting. But happy to tell you about that if you want to stick around. But I'm going to turn off the streaming, and we'll pick this up on Wednesday.